Integrating is, at its heart, a creative process, right? Differentiating is just applying a bunch of rules carefully, but just applying the rules. Integrating usually requires some sort of creative flash of insight. For u-substitution in particular, there's a ton of creativity in picking the best u. So if you're looking for how to pick u, right, what should you make u equal for your u-substitution? Well, I'd look for things that you can grab as du, right? Try to find pieces of the integrand that look like the derivative of something. Well, let's try that. So let's try to anti-differentiate, say, x over the square root of 4 minus 9x squared dx. So I can see that x squared in the denominator, and I can see an x in the numerator, and I'm thinking, I'll put the x squared in the u so that the du will grab the x in the numerator. Let's go. So I proposed that u should be 4 minus 9x squared, and then what's du? Well, calculate the differential of u by taking the derivative here, and the derivative of 4 is 0, but the derivative of negative 9x squared is negative 18x. I'll include the dx. And now you're thinking, oh, this is terrible. I don't see a negative 18 anywhere in this problem, but I can introduce one. I can make a negative 18 there as long as I cancel it with 1 over negative 18 there. So I've done nothing to the antidifferentiation problem. I haven't changed the problem at all. This is just multiplying by 1 if they cancel. But I've now got a du in my integrand. So let's make that substitution. This is now, well, the numerator is now just du, and the denominator is the square root of u. And I want to make sure to include the 1 over negative 18 in front. And that integral I can do with the power rule. So this is still 1 over negative 18. And what's an antiderivative of this? Well, this is the antiderivative of u to the negative 1/2 power. But that is exactly the sort of thing I can do with the power rule, right? So this is 1 over negative 18 times, by the power rule, this is u to the 1/2 over 1/2 plus c, which I could rewrite a little bit more nicely. Dividing by 1/2 is the same as multiplying by 2. So this is negative 1/9 the square root of u plus c. Now I'll rewrite that in terms of x. So in terms of x, this is, well, remember, u is 4 minus 9x squared. So this is negative 1/9 the square root of 4 minus 9x squared. That's what u is, plus c. So I found an antiderivative of x over the square root of 4 minus 9x squared. I should warn you here, something that makes antidifferentiation so hard is that similar looking integration problems can have totally different looking answers. For example, we just saw how to antidifferentiate x over the square root of 4 minus 9x squared, and we got this. How will we antidifferentiate this very similar looking function, 1 over the square root of 4 minus 9x squared? The only difference is that I got rid of the x in the numerator. But that's a big difference. That x in the numerator was facilitating the substitution. I needed that x there in order to have something to fit into the du. Without that x there, what am I supposed to do? Well, I could try to factor out 2 from the denominator here. I mean, I'm not going to make a substitution yet. I'm just going to try to rewrite the integrand. So if I factor out a 2, this is the antiderivative of 1 over 2 times the square root of 1 minus 9 over 4 x squared dx. And you might be wondering, why is there a 2 on the outside and a 4 on the inside? Because the square root of 4 is 2. My plan here is to make the denominator look like the square root of 1 minus something squared. Rewrite this integral again as 1 over 2 the square root of 1 minus, and instead of 9/4 x squared, I'll write it as 3/2 x squared dx. And now I'll make a u substitution. I'll set u equal to this 3/2 x. So 3/2 x, so that du is 3/2 dx. And now you're going to complain, well, I don't see a 3/2 dx. Now you do have a 1/2 dx here, and I can manufacture a 3 here as long as I'm willing to put a 1/3 on the outside. That doesn't affect anything. But now I've got a 3 dx over 2, so I've got a du, 1 over the square root of 1 minus u squared. Well, let's write that down. So this whole thing is 1/3 the antiderivative of 1 over the square root of 1 minus, this is u squared, and 3/2 dx is du. Why is this a good idea? Well, this is a good idea because this is now 1/3, and I know something which differentiates to this. Arc sine u, right, is the antiderivative of this. To finish this, I'll replace u by 3/2 x. So I get that this is 1/3 arc sine of 3/2 x plus c. This is just because u is 3/2 x. Look at how different this experience was compared to that first integral that we did. We just showed that the antiderivative of 1 over the square root of 4 minus 9x squared is 1/3 the arc sine of 3/2 x plus c. And that looks totally different from antidifferentiating x over the square root of 4 minus 9x squared, right? I didn't need any inverse trig functions there. You know, even though the integrands look relatively similar, right? I mean, I'm just missing an x, but it totally transforms the answer. Picking the best u for your u substitutions really is an art form. This is why people have integration bees just like they have spelling bees, right? There's a real creativity to integrating.